So, in this lecture we speak about mode superposition method. So, when you talk about multi-degree freedom system model, I can say my equation of motion can be written as see here, and the size of these matrices depends on the degree of freedom. They depend on the degree of freedom. Usually the mass or lumped mass. The moment I say lump the mass at the same point where I am measuring my displacements, then I am expected to get a diagonal matrix of mass. Of course, in offshore structures, as you have seen in second module, there can be off diagonal elements present in mass matrix despite you measure the responses in the same place where degrees of freedom are marked. And of course, look at the K matrix because of the dependency of coefficients of stiffness matrix on the response, which is an integral built up, because now this equation of motion cannot be solved explicitly. There is a dependency on left hand side to the right hand side of this equation, because f of t, if you look at the Morrison loading, it demands the water particle kinematics which has got relative motion of the vessel or the body of the offshore structure. Therefore, x is required to compute, or x dot is required to compute f of t even, and x dot is not known because there is a one of the unknown here. Now, instead of looking at the forced vibration responses, we always ultimately interested in finding out the response vector, which essentially comes from different modes. Now, one may wonder that why one is interested in knowing responses in different modes. For example, the moment I say mode, I have got two inherent characteristics which is assigned to this. One is I will know at what frequency this response is activating or contributing, and of course I will also know the relative position of the mass points when the system is vibrating at this specific frequency. So, I will know what would be the relative position of the mass at this frequency. So, I can easily find out if this frequency matches with my excitation frequency. I can always expect that the damage is going to be maximum, and by knowing the mode shape I can always know where will be the local damage focused, because I know the relative position of the mass movement. So, the response always is contributed from different modes. Now, the question comes, if in a multi-degree freedom system model, if the degree of freedom is very large, practically let us say infinitely high, do we have to consider all the modes for working out my response? Now, the question comes, how many modes do I consider for finding out my response summation? Let us say x be any arbitrary vector. Let x be any arbitrary vector in n dimensional space where n talks of the degree of freedom. Then I can write this x as simply summation of r equals 1 to n qr of t phi r, which I call as phi q. Let us say equation number 2. Equation number 1 was the equation of motion which we had in the previous right. Now, in this case obviously phi is the modal matrix, each column of this matrix represent mode shape. Mode shape of the MDOF system. And Q, the Q is a vector of modal coordinates which is relating to the system coordinates. We will come to this. We will come to this. Now, my equation of motion of MDOF system is given by, let us say, mx double dot cx dot kx is f of t. I pre multiply this with phi transpose. And also substitute equation 2 in the above, that is x is a vector multiplier of the modal mass matrix or the mode shape matrix. So, therefore, I can say phi transpose m, x is phi q. So, I should say this is going to be phi q double dot plus phi transpose phi q dot plus phi transpose k phi q as phi transpose of f. Let me call this equation number 3. Now, the mode shape phi for orthogonal matrices mode shape phi for orthogonal with respect to m and k will result in a diagonal matrix. Okay, will result the multiplication into a diagonal matrix. This multiplication, for example, they will become diagonal. Let us write each one of them for an rth mode separately and see what happens. For example, for rth mode phi, let us say R transpose M phi R. I am going to call this as MR star, which represents the modal mass for the rth mode. Similarly, phi R transpose C phi R can be called as CR phi, which represents the coefficient of viscous damping in rth mode. Similarly, phi R transpose K phi R, I call this as KR star, represents modal stiffness in rth mode. Phi R transpose F is called as FR star, which represents the modal force in rth mode. All these equations I am calling them as 4. What I have done is, from this equation 3, I just wrote a typical equation at an rth mode and see what is happening, each one of the terms. I will now apply a special condition to this set of equations 4 and see what happens. That condition what I am going to apply is, if the mode shapes are mass orthogonalized then you can orthogonalize it with respect to stiffness also, then MR star, what will happen to MR star if it is orthogonal with respect to mass matrix? Sorry, 1. CR star, I am expanding C as ratio of the critical damping. So, 2 R zeta omega. So, this becomes 2 zeta R omega R, and KR star will give you the natural frequencies, is it not? Now, okay, I will write this as equation 4a. These are all actually special conditions of these values when the mode shapes of phi remains mass orthogonalized. Now, based on 4a, I can now write an expression for modal participation factor. We will see what is the importance of this factor. Now, I can find what is the modal participation factor in rth mode, indicated by gamma r, which is given by phi r transpose mr. R is a multiplier here, not a suffix. Phi r transpose m phi r, equation number 5. Before I want to find the modal participation factor, I want to know what are all the modal mass present in every mode, because I have given equation set of equations for 4 saying that what would be the modal mass in the rth mode. I would like to know what is the modal mass in every mode, because depending upon the conditions implied on the modal mass, I can truncate the modes. How many modes I must look at? If there are n degrees of freedom, I will get n mode shapes and n frequencies. Should I use all of them to find out? So there are two ways of looking at it. One, estimate the modal participation factor, use this factor on every mode shape and then get their x value. The other way is truncate the modes depending upon what is your modal mass participation in the whole system. Why we are talking about mass? Because mass is the major source of contribution, because this is giving me the inertia force to the system. Okay, I am not talking about the restoring force. Of course, this is a dependent on these two, so we do not talk about this, because there can be systems which can be undamped also. But this gives me the inertia force, which is predominant for dynamics. I already we discussed, even though the response be time variant, even though the excitation force be time variant, but if the system does not have a reproductive mass, indicative mass, which can give you or produce good substantial significant inertial force, we do not do dynamic analysis. For example, I have a paper which is floating, the motion of the paper is in a time domain variant, the force which I am blowing like a wind is also variant. I do not do dynamic analysis to trace the response of the paper, because paper has no mass actually. Okay, the inertia component will significantly remain absent. So I focus on the modal mass participation. Okay, so we will quickly work out an example to find how will I get m1, m2, m3 for this example. Then I will take it forward to talk about truncation of modes after we understand this example. Any questions here? I will use this equation later, I will take away this now. So let us say I have an example of a 3 degree freedom system whose mass is given as in tons, and of course we have the modal matrix, which we know how to get, but anyway I am giving the values if I know my k and m. This is 6.26 and 12.10. Can easily make out there are no zero crossings, there is one zero crossing here, there are two zero crossings here. So first mode, second mode and third mode. The corresponding frequencies 3.88, they are in radians per second, 9.15 and 15.31. So we already know mr star is given by phi transpose m phi. So, can you find out m1 star, m2 star and m3 star? So, if you want to find m1 star, I must use phi 1, phi 1 is the first column, I have to use a transpose of this. So, 1.55 and 0.2 multiplied by the mass matrix, which is 30 0 0 30 0 0 0 30, and multiplied by the vector, which is 1.5 and 0.2. You can see the compatibility. This is 1 of 3, this is 3 of 3, this is 3 of 1. You will get only one value, okay, which can be quickly worked out. Is it 40.275? So, this is 40.275. Similarly, work out for M2 and M3. Yeah, fine. I will give you the answers. It becomes 122.019, 122.019, and M3 becomes 5597.93. Okay. Having said this, now let us see how do we truncate the modes, what will be the condition for truncating the higher modes, where do we stop, what is it, frequency governed or is it mode shape governed, what would be the effect in nutshell in dynamics if you truncate them, can this error be corrected, because you very well know you are creating an error because of truncating the upper modes, can you correct this error, this is called static correction. We will see that also. Remove this, then I will take up the same example and apply it on a different perspective. Now what we are talking about is the mode truncation. So what we have learnt in the A part of the lecture is that we know how to find out the modal mass contribution in every mode. In an rth mode I know what is the contribution of mass from the equation. We also studied an equation which gives me the modal participation factor. Okay. Based on these two understanding, I will take forward and see what will be the logic to truncate the higher modes. So we already saw in a multi-degree freedom system there can be many number of modes, all of them need not be used. Now the question is where to use them, where do we need them actually. So if you look at the response, we wrote in equation 1 earlier, I will rewrite it again. We said the equation is varying from r to n, which is having qr of t and phi of r. I am reiterating this equation because n becomes the degree of freedom. I am rewriting it saying, do not you take it till n, take it only till n hat where n hat is far lower than n. I am truncating it. Now the question comes, what are the factors which will govern how many modes should I include? What should be the n value? N value for a 6 degree freedom system is 6, for a 30 degree freedom system is 30. N hat can be any number of your choice, lower than 30 or 6, okay, can be very much lower if n is very high. For example, 1000 degree freedom system model you have, you can pick up only 10, 20, can be very much lower. Now the question is, how many modes, how many numbers you desire on n hat, what will be the factors? The factors which will decide the number of modes to be considered in your response computation. Remember, we are talking about the response computation, right? The number of modes, that is required in response computation depends on many factors. 1, all modes whose frequency is lower than omega n, sorry, whose then omega star is to be considered. Now the question comes, what is omega star? Omega star is the highest frequency of the forcing function, that is the highest frequency content of the forcing function. You must pick up the frequency till that. Two, the second condition also important, at least 90% of the total mass of the structural system should be represented. Where do we check this? This can be physically seen, because for a multi-degree freedom system model, the classical eigensolver will give you different frequencies. You can always physically check that a frequency is not omitted, so that omega star is not deleted from your system. You can always pick up those number of modes you can do. How will you check the second condition? The second condition similarly says that the cumulative effective modal mass, it leads to the cumulative effective modal mass. Is simply sum of r is the number of degrees you are considering, mr star gamma r star. For all modes, and this summation should not be less than 90% of the total mass of the system. Now in this equation, mr star is already known to me. I have got equation set of equation 4a which can give me MR star. Equation 5 gave me the modal participation factor at an rth mode. So, if I know this and sum them up, if that sum should not be lower than 90% total mass of the system, I can truncate the remaining modes. Okay. Now, let us see how do we correct this error, because this will result in error. Okay. We can correct this error, this is called static correction. Any questions here? The moment I truncate the modes, I will result in error. Okay. I can correct this error, this is called static correction. Why it is called static, I will come to that. We are talking about dynamic analysis. Why it is called static, I will come to that. What are you correcting? You are correcting for higher modal response. I mean, you are not including the response from the higher modes, you are applying correction to them. Okay. Let us see how. Now, let us consider the following equation. X is given by, X is my response, which is given by R equals 1 to n hat. N hat is a truncated mode I am having, which I say it is phi r vector of q r of t plus n hat plus 1, the next mode till n. Okay, I am just separating this phi s q s of t. Call the equation number, so 1. Look at the second term of this equation. The second term of this equation actually represents the error. Due to truncation of modes up to n hat, isn't it? Originally I have n modes, but I am truncating them to n hat, where n hat is much lower than n. Having said this, let us come back to my equation of motion. I am talking about this part, so I am using s suffix here. Okay. ms q double dot t, because my response is no more in x, I am converting into q, because that is a multiplier value of phi. Okay, the general expression plus cs of q dot of t plus ks of q of t, which I of course call as fs. The suffix s says that I am not looking at the original equation of motion, I am looking only at the error created by this part alone. From this equation I can write q s of t, this is s, which can be simply fs by ks minus q double dot of t, I have to divide it by m as well as by k, isn't it? I will get omega s square minus c is of course proportional damping is put to critical, I can say 2 zeta s q dot s of t by omega s. Is that okay? Because this is 2 zeta omega n, k by m will have omega square, I get omega n at the bottom here. I call this is equation number 2 and 2a. Now look at the equation number 2a here. there are two interesting observations I can make from equation 2a. One observation is the response q which is caused from the error term here depends only on the static response, okay. That is why it is called static correction. For any value, increased value of omega, you will see there will be a depletion of these terms, is it not? They will keep on decreasing because it is inversely proportional to square of that. The dynamic term which comes from inertia is inversely proportional to square of higher omegas, and the damping term proportional to inverse of omega. For any higher values of omega, these terms will get deleted, they will become insignificant, okay. That is why I call, if I correct this to this, I call this correction term as static correction, okay, because this is having only static term here, there is no dynamic term involved in this, is it not, okay. Any questions here? I will take away this. Having said this, we can put a word here saying the response from higher modes will be decreasing due to insignificant contributions from dynamic response terms. Therefore, the response in higher modes can be approximated only to static response. What does it mean is, in the higher modes I do not have to look at the dynamic content of the response. Having agreed upon that I will look only at the static correction, the numerator has f of s in the static correction, okay. Let us work on f of s now. We already know the modal force, equation 4a will give me f of s as phi of s of t, sorry, it is not, it is a vector, phi of s of t capital F, okay, small f, that is my f of s. Now I am looking for my response. So x already I know, summation of r to 1 of n hat, which is phi r q r of t plus summation of n hat plus 1 to n, which is I call as s 1 by k s of, I had a numerator f of s, I am replacing it with phi s of phi s transpose f, is that okay? Which can be now rewritten as summation of r to 1 n hat phi r q r t plus summation of S to n. Can I say this as Fs of f? Where 1 by Ks of phi s of phi s transpose is what I call as Fs. What does it represent? This represents this term represents the contribution of sth mode towards, I can write it here, I will remove this, towards the flexibility of the system. Why I am saying flexibility? It is 1 by k. Okay. Now there is a small problem here. The issue is, you may agree to truncate the modes from n to n hat, where n hat is much lower than n, but to evaluate f of s you require the full mode shape, because f of s wants the mode shape from S, which is nothing but n hat plus 1 to n, is it not? But f of s require estimate of modes from n hat plus 1 to n, is it not? Otherwise I cannot compute this, because the S is summation from n hat plus 1 to n. So there is no benefit actually I am getting, because anyway I am working out all the modes. Okay, how to get rid of this problem? See, my original problem is I do not want to compute all the modes. I agree I can truncate, I can do a static correction. So when I say static correction can be applied, because the dynamic effects in higher modes are not responding or represented, when it is agreed upon, when I start evaluating f of s, I require this s value which is contributing from n hat plus 1 till n. It means practically I have to have all the modes in front of me. Okay. This problem is intelligently get rid of in the dynamics. See how we are doing it. Are you understanding this issue? This does not give me actually a benefit, because though I am truncating till n hat, but I require phi for working out f of s, which is a static correction if you want to account for the errors of response in the higher modes. These errors does not arise from dynamic effects, but there is a static error coming from this which I got to correct. To correct that I need all the modes. Okay. Practically if you have all the modes, there is no question of doing any truncation at all, is it not? Right. How will you get rid of this? Having understood there is a complexity here, we will move forward and see how I will get rid of this problem. Let me now pick up that term only which is S of n hat plus 1 to n of 1 by Ks phi s transpose I can rewrite this equation as K inverse minus summation of terms from r to n hat 1 by k r phi r transpose. What I am trying to do here is, instead of looking for the correction in the higher modes, I take the stiffness or the flexibility for the whole system and subtract the correction from the lower modes. You see, I am doing only from n hat, and till n hat I know this value. Okay. So, I do not have to compute the mode shapes beyond n hat till n. Okay. I can rewrite this equation as k inverse minus r equals 1 to n hat, which I call this as Fr, is it not? That is an F term here. We said Fs, this is Fr. So, it is interestingly the above equation does not demand computation of higher modes, is it not? Therefore, x can be said as into, of course, F, there is a multiplier here, right. This is what we call as static correction. Some literature address this as missing mass correction. Okay. What does it do? This accounts for response in higher modes, is it not? That is what it is doing. Interestingly, this only takes care of from the lower modes. That is the beauty of this whole experiment. I am not touching on the higher modes at all. I am truncating at n hat, but still I am making a correction which accounts for higher modes. That is the beauty of the whole exercise. Okay. I can stop at n hat. Now, the question again reiterated is, where will I stop my n hat? Two cases, I must check for the frequency which will be either equal to or lower than the highest frequency of the excitation force. I must look till that part, and I must look at the modal participation from the mass should be at least 90% of the total mass. Okay. If these two conditions are satisfied, then I can truncate the modes at n hat, apply this correction, this will automatically account for the error what you have obtained from the higher modes. X of t can be interestingly done. So, in the next class we will take up an example and see how the truncation of modes can be applied for, let us say, a 4-degree freedom system problem. Do you have to take all the 4 or only 2 or only 1? We will see by demonstrating this in 2 examples. Okay. that is the focus in the next class. Any questions here?